So in this lecture, we continue talking about how to formulate an optimization problem. And now we want to focus more on a real-world example and try to build on that. So first, let's have an overview of what we discussed. We mentioned that an optimization problem has three components: objective function, constraints, and variables. We also talked about different scenarios and when having an optimization problem makes sense. That was the scenario that number of variables are greater than number of equality constraints. All right. Before starting today's lecture, I want to talk about some applications that you can use optimization to solve a problem. First is cost minimization. All right, cost minimization has a wide range of applications. It starts from simply going to a grocery store. You have a specific amount of money and you want to minimize your total cost given a certain number of orders that you want to place. Second, it's in data centers. Assume that you have 10,000 data centers and you want to minimize the cost of energy subject to optimizing the way that these data centers are operating. You want to switch the load between them to make sure that the energy is minimized. The second application is benefit maximization. Assume that you have a certain business. You're supplying a certain product to the market. Your goal is to maximize your benefit given certain constraints. For example, one of the constraints could be satisfying the demand of customers. The third application is data classification. So data classification is one of the promising applications that we can use in several daily applications. For example, in real-time autonomous decision-making, you have to classify. When a robot wants to decide whether it should go right or left, they somehow are running data classification on the images that they record. The fourth application, machine learning. So if you learn the fundamentals of optimization properly, you can deploy them in machine learning algorithms. A lot of machine learning algorithms rely on solving an optimization problem and then determining the optimal solution. Next one, reliability optimization. So assume that you want to design a system and you want to have some level of redundancy in that system. So formulating an optimization problem can help you to identify the optimal design for that system. Data fitting. Assume that you want to fit a curve to a given set of points. So you have some data points and you want to fit an optimal curve. What you are going to optimize is the distance of all of these points from your expected curve. Let's say alpha x plus beta. So these are some of the applications. Also, there are some engineering applications for optimization, such as power system optimization. Assume you have some generators, you have some electricity consumers, and you want to optimize the cost of providing electricity to these consumers. Another one, transportation networks. So in transportation networks, you can optimize the cost of driving from point A to point B, given the constraints such as traffic congestion, the time that you want to drive, and the cost of gasoline that you want to pay. So as you can see, there are several optimization problems that we deal with in our daily life. Sometimes you're making a decision while solving an optimization problem. Maybe you don't notice that that's an optimization problem, but you're formulating and solving in real time thousands of optimization problems in the daily life. So now let's look at an example. We want to start with a basic supply-demand problem. So our goal is to find the optimal point where supply and demand are equal. Before going further into the details, let's look at the way that we can write an optimization problem. There are two categories: unconstrained optimization . Unconstrained optimization is like minimizing a function. So we write it with this notation: minimizing or maximizing. Minimizing f of x, and we write the variables here. So this is your optimization variables, and this is your objective function. All right. This is called unconstrained optimization because it doesn't have any constraints. The second type is constrained optimization. For the constraint optimization, let's say it's minimization, minimizing f of x, variables are x, subject to. After subject to, you write all of the constraints. G of x is 0, and h of x is less than equal to 0. All right, so this is called equality constraints, and this one inequality constraints. All right, another type of optimization, as I mentioned, are maximization problems. So instead of this minimum, you can have maximizing f of x. Same, instead of this minimum, you can have maximizing f of x. So this is the way that an optimization problem looks like. Now let's go back to our supply demand for a certain example. So, example, supply demand balance with two suppliers A and B given total demand. So the reason that I chose this problem, because it can be expanded, it can be generalized to several real-world examples. For example, you want to you want to record 10 terabytes of data on two data centers, data center A and data center B. So your demand is 10 terabytes, your suppliers or your service providers are the two data centers A and B. So first we have to see what's our objective function. Here in this problem, the given information, for example, it can be cost of storing data. It can be cost of generating a certain product. Your cost function for supplier A and B is f of I. P of I is equal to AI pi square. All right. And your total demand that should be satisfied using these suppliers is P of D. Our variables are P of A and P of B. So what P of A is the total production of supplier A, and P of B is the total production of supplier B. All right, let's get to the problem formulation. Now here is what we have. We have the supply side and we have the demand side. At the demand side, we have total demand of P of D. At the supply side, we have total supply of P of A and P of B. All right, so now we are going to formulate different instances of this problem. Case 1. Our goal is to minimize total production cost. All right, and our constraint is, so this is our goal. Our constraint is demand supply balance. All right, so it's going to be minimizing f of A, P of A, plus f of B, P of B, subject to P of A plus P of B is equal to P of D. So you already know what's f of A and f of B. How do we know that? That's given in the problem specification. And where does this constraint come from? At one side of this balance, you have total supply, which is P of A plus P of B. At the other side, you have the total demand, which is P of D. Let's go back to the data center problem. Let's say P of A is the total capacity, the total storage capacity that the storage unit A can offer. And P of B is the total storage capacity that storage B can offer. So sum of these two should be equal to the total demand that we have, or P of D. In our case, it was 10 terabyte. Now let's look at another instance of the same problem. In this case, we want to enforce more practical constraints. So what's our constraint here? For unit A, we have a maximum production limit of PA max. All right, let's rewrite our optimization problem. Minimizing total cost of generating P sub A units from unit A plus total cost of generating P sub B units from generator B or supplier B, subject to, we have the balance equation, and we have a new constraint. We have a new inequality constraint. All right. What does our new inequality constraint tell us? It tells us that P of A cannot exceed P of A max value. All right, now let's take a look at a little bit more complicated example. Example 2. Example 2, formulate an optimization problem to find the dimensions of a rectangle with area 40 meters square whose perimeter is as small as possible. So for this problem, first we have to define our rectangle. So we draw a rectangle. We define the dimensions as A and B. So what are our variables? Our variables are A and B, width and height of the rectangle. So our objective is minimizing perimeter, and our constraint is subject to the area is 40 meters square. Let's try to write this mathematically. So our objective is minimizing A plus B plus B, which is our perimeter. Our variables are A and B, and our constraint. So what's the area for rectangle? It's A multiplied by B. Is A multiplied by B is equal to 40. So this is the optimization problem that we can formulate to find a rectangle with area of 40 meters square with perimeter as small as possible. Now I'm going to add another constraint to this problem. So formulate an optimization problem to find dimensions of rectangle with area 40 meters square, perimeter is as large as possible. Further, sum of A and B is less than 15 meters. All right. So this time, if you go back to the previous example, we wanted to find the minimum perimeter. But in this example, we want as large as possible. So we are going to have a maximization problem. So maximizing A plus B plus B, this is the perimeter of your rectangle because you have A, B. Your variables are A and B, subject to. Again, the area is 40 meters square, so A multiplied by B is 40 meters square. You have a new constraint. What's your new constraint? Sum of A and B is less than 15. A plus B is less than 15. So this is your optimization problem. As you can see here, we have one more constraint and we have a maximization problem. Another example, which is more practical, is data analytics. So I'm going to talk about example 3, data analytics. Support vector machine. So our objective is to maximize the margin between two or more classes of data. Okay, let's consider I have some data here, I have some data here. I call this class A, I don't call this class B. You have a plane here, you have a plane here. This line between these two classes is W transpose X plus C. So this is a given function. If this function is greater than or equal to 0, we have class A. If it's less than 0, we have class B. So in order to maximize this margin or to make our data analytic solution more accurate, we are going to formulate a generic objective function. So this is the goal for support vector machine. Support vector machine. Maximizing 2 divided by W transpose W subject to Yi Wt xi plus c greater than equal to 1. And your variables W and C. So if you look at this, it's going to determine W and C, which are the two coefficients to find this margin, to find where is your optimal classifier. So again, you're going to learn more about these details in data analytics course, Introduction to Data Science, and so on. But as you can see, there is an optimization problem behind this. An optimization problem where one wants to maximize the margin between classes subject to all data samples are in proper class. So we want to ensure that this distance between our two classes is maximized. Also, we want to make sure that most of the data is in the right class. So this was all for introduction to optimization and how to formulate an optimization problem. I'm going to review the major content that we discussed. We talked about components of problem. The reason that I'm emphasizing on this because this is very fundamental and important for the next steps of this course. I want you to learn how an optimization problem looks like and how we can formulate an optimization problem based on a real-world example. Objective, let's call it f of x. Constraints, that could be inequality or equality constraints. Inequality, we can show it by h of x less than equal to 0. Equality, g of x equal to 0. And then we talked about mathematical formulation of an optimization problem. It could be either minimizing or maximizing f of x with variables x subject to constraints. Constraints are either equality or inequality constraints. We also talked about applications of optimization in several computer science and engineering problems, including machine learning, data science, power systems, transportation networks, and so on.